Okay, and yeah, let's go back to linear algebra. Sorry for late. And here is some idea we talked about last time. So we start talking about the idea of a subspace. So subspace is a subset of your vector space that is also a vector space. Okay. And so you need to check two things to make sure that your subset is a vector space also. So you need to check it's closed under the operation. So you need to check closed under scalar multiplication, and you need to check that they are closed under vector addition. And then we talk about two vector space that will be very useful. One of them is the null space of A, so it's a solution set to AX equal to 0. And then we start talking about the span of the set of vector. So you can take any set of vector from your vector space, and they will define a subspace. Okay. So the span thing is all possible linear combination of the set of vector you pick. So pick a set of vector and think about what are all the possible linear combination from them. That set is it's another set, and it will be a vector space. It's called a span of those vectors. And then there is the other way of this direction. So you got a subspace. You can always find a spanning set of it. So it's just a set of vector where the span is your subspace. And there are many spanning sets for the same subspace. Okay. And I guess let's go back a little bit. We have a whole bunch of wordings for this spanning. For the set of vector and vector space relationship. So if a span of this set V1 to Vn equal to some subspace V, and so there are 5 wordings that we kind of copy from Wikipedia. So first we can say this set of vectors span V, or we can say, no, this is just past tense. We can say V is spanned by this set of vector, or we can say this set of vector is a spanning set of V, or there are other wording with this name generate. This is what people like to use when you are doing more advanced algebra. They will say V is generated by this set, or this set is a generator or generating set of V. Okay, so here are some wordings of this some set being span of your V. And then let's keep going forward about here, I think. Okay. And then we talk about, okay. And now we go to 3.3. And now we care about this idea of minimum spanning set. So we just talk about span, but we see that some set of vector, when they span a vector space, some elements are not needed. Okay, so maybe you only need V1 from V1 to Vn minus 1 instead of V1 to Vn, and you will span the same subspace. Okay, and I guess we have a bit of example in maybe here. Okay, okay, so we have an example here saying that well, if V3, we actually use x3 here. So x3 is a linear combination of x1 and x2. Then any linear combination of x1, x2, x3 can be just written as a linear combination of x1 and x2, because this x3 component can be written as some x1 and x2 once again. Okay. And so we want to see when does this not happen. And what we get is that there are 3 conditions that are equivalent. Okay. And so first one is well, we kind of write this in a negative way. Yeah, so, yeah, so the first one is that this set of vector V1 to Vn is not a minimum spanning set. Okay, not a minimum spanning set. We have a kind of a statement with a negation here, kind of because it's easier. Okay. So now so these 3 statements are equivalent. First is that they are not a spanning set, and then the second one is that there is some Vi that you can write it as a linear combination of others, And then in our proof, we'll just assume this Vi is Vn because really any one of them is the same. Okay. And then there's a third condition that will be very useful. This condition we'll keep doing throughout this chapter. It is when this equation has a non-trivial solution on C. So I guess here I should say on those set of Ci. Okay. And so first we need to say why does this, we'll say non-trivial because there's a trivial solution. That is, you just pick all the scalars C1 to Cn here as 0, then this equation will always be satisfied. But if this equation is satisfied with some non-trivial set of C, so just not all of them equal to 0, and then we will have those two conditions. And this condition is so important. This is called linearly dependent. Okay, linearly dependent. Do we have a ly? Let me take a peek. Linearly dependent. Okay, so it's correct. Okay, so dependent. Okay. And so yeah, so we have an equivalence of those three conditions. And in our proof, we'll prove we'll prove a lot more than enough, more than we need, because usually you only need to prove 3 things to prove that 3 things are equivalent. But we're going to prove 4 things. We're going to prove that we can go from A to B, B to A, and we can go to B to C and C to B. Okay. And yeah, and all 3 conditions are equivalent. Okay, and so next time we go over 3 of those 4 proofs here. Okay, so let's go through them quickly. Just once again. So first we go from B to A, and we say if there is some Vi, so it's assume that Vi is Vn. If Vn can be written as a linear combination of B1 to Bn minus 1. Then just like in our starting example, then any linear combination of B1 to Bn, then you can change this Bn to once again B1 to Bn minus 1. Then you just have a linear combination of B1 to Bn minus 1. Okay. So you see that this thing is also inside span of B1 to B just n minus 1. Okay. And yeah, so everything in this span of B1 to Bn is is this form of V, and it's inside this span V1 to Bn minus 1, so we know that those 2 things are equal. And I guess if you really want to prove 2 sets are equal, there is another trivial thing you need to prove. So from here, we just prove that this span of n is inside span of n minus 1. Then the other way is trivial. You can easily see that span of n minus 1 is inside span of n because this is just a smaller set. Okay. And okay, so let's prove B to A, and then we need to prove A to B. So this is not in book, but actually quite simple. So we want to say if we say this V1 to Vn is not a minimum spanning set, and let's say remove Vn will give us 10 span. So span of V1 to Vn equal to span of V1 to Vn minus 1. And then then we just look at this Vn here, and obviously Vn is in this span of V1 to Vn because it's a linear combination of this thing with coefficient always 0 except coefficient 1 on Vn. Okay? So it's inside this span, and just by our definition, this span equal to this span. Okay, so this span of n equal to span of n minus 1. And so obviously Vn is inside span of V1 to Vn minus 1. And this is exactly what we want to prove. We want to say Vn can be written as a linear combination from V1 to Vn minus 1. Okay. So see this once again. We say Vn can be written as a linear combination of our n minus 1 vector. And it's inside this span, and by definition of span, it's a linear combination of V1 to Vn minus 1. Okay. So yeah, so we prove A and B are equivalent, and B and C being equivalent. We already see this last time, but let's see it once again. So let's say Vn can be written as a linear combination of V1 to Vn minus 1, and then we want to make it into equation form of just whole bunch of c times ci times vi sum to 0. Then we just move this equation around. We just move this to other side, and then we have this equation equal to 0. Okay. And yeah, then we just rename those alphas equal to c, and we get so alpha 1 equal to c1, alpha 2 equal to c2. And then only different thing is then now we also have this cn. So cn equal to -1. So we have alpha 1 to alpha n minus 1 equal to c1 to cn minus 1. And cn equal to -1. And because cn equal to -1, this also satisfies that cn is non-zero, because as we say, we want this to be a non-trivial solution. So we must have one of them not being non-zero, and here this -1 is non-zero. So yeah, so we satisfy the condition C. And lastly, we have condition C from B. And once again, the whole bunch of thing and one whole bunch of C, one of them is non-zero. And we just assume Cn is non-zero like before. Cn, we assume Cn, the nth one is the weird one. And if Cn is non-zero, then you can divide everything by Cn. And if you move things around, you see Vn equal to this minus Ci divided by Cn times Vi and summing together. Okay, so that's a proof of everything. And here is the theorem again. Okay, and yeah, so the theorem will be very useful as a basis for the next section. Okay. Yeah, so the three are equivalent, and then we have a more, as we said, we have more definition on this condition, and this condition is called linear dependence, linear independence, and yeah, and yeah, and it's so important. We have two names for it, both itself and its negation. And so linearly independent means that this equation C1V1 plus C2V2 plus all the way to CnVn equal to 0 vector. This equation only have the solution that, so you want to solve this equation for C1 to Cn, where you fix V1 to Vn. And if this solution only have this equation only have the solution that C1 equal to C2 to Cn equal to 0, then this set of vectors, so this condition you set, this V1 to Vn are called linearly independent. Okay. So this is the first time we define something like this. So you define the property of the set of vector by saying what you can do on a solution of some equation that involving those vectors. Okay, so we say we have this equation with this V1 to Vn vector, and yeah, if the solution set is only the trivial zero solution, then we say this set of vectors are linearly independent. Okay, and yeah, and then as we say, we have the negation of this property. Then this set of vector, if we will say they are linear dependent, if this equation C1, this linear combination equal to 0 equation has a non-zero solution. Okay, so you have a non-zero solution. And as we said, this is called a linearly dependent, and it's exactly this condition. Okay, and now with this condition, we have a bit better thing to say. So this is called linearly dependent. So if we, okay, so yeah, so this is linear dependent. So if we take a negation of A and a negation of C together, then negation of C says that V1 to Vn are linear independent, and then the negation of A says that V1 to Vn is a minimal spanning set. Okay. And yeah, so here we have a not here, and if negation is not, then we have the V1 to Vn is a linear spanning set, minimal spanning set, and so we go back, so we fulfill what we want at the start of this section. So start of section we want to say what's the condition of V1 to Vn is a minimal spanning set, and now we see that it's a minimal spanning set if only if you are linearly independent. So we have this, And minimal spanning set for your space will be called space or subspace will be called basis. Okay, and yeah, minimal spanning set means that you cannot remove any vector from your set to still span your space. Yeah, and yeah, so next chapter we'll be talking about basis, and we have the first and one of the very important theorem for basis. That is, you want to be a basis, then your vectors need to be linearly independent. Okay. Yeah. So yeah. So here is a bit of recap of last time. So the basis, and I guess this is so much we want to talk about basis, and so we can kind of forget basis now for now, and now let's talk about linear independence. Okay, so this section is actually about linear independence, and now let's go through some example of linear independence. And so first is this two-dimensional example. So we want to check whether vector 1, 1 and vector 1, 2 are linearly independent or linearly dependent. And as we say, we want to check a solution to this equation. So we want to say C1 times our vector 1, C2 plus C2 times our vector 2 equals 0, 0, and does this has a non-trivial solution. And so this, if this vector equal to this vector, then every coefficient need to be equal, and so we can write down two equations here. So on this first coordinate, we have C1 plus C2 equal to 0, and on this second coordinate, we have C1 plus 2C2 equal to 0. And if you solve both of these equations together, you need to see that C1 must equal to C2 equal to 0. So those two vectors are linearly independent. And yeah, so this example is something we'll do later part of this of this section. Is we'll keep writing the equation. We will see that determining whether vectors are linearly independent or not means that you need to solve some linear system of equation like this. Okay, we will talk about this more later. But for now, let's check more linear independence. And now we have 4 vectors and want to check whether they are linearly independent or linearly dependent. So the 4 vectors are x equal to 1, 2, 3, and e1, e2, e3. E1, e2, e3 are the standard vectors. Okay? And once again, we just use this c1, c2, c3, c4 equals 0 and solve this equation. And we see that we can find a solution to this equation such that they are not all 0, and but this summation equals 0 vector. And here you can kind of see C2, C3, C4 are quite free here, so you can just so I guess it's another way around. So C1, we kind of view C1 being equal to free. So we have C1 being arbitrary, and just pick corresponding C2, C3, C4. And yeah, so these settings will make this equation satisfy, and then this set of vectors are linearly dependent. And yeah, we already seen before that this is not a minimal spanning set because E1, E2, E3 already span the whole R3. Okay, and the next time we have the geometric interpretation. So two vectors are linearly, so if we are in R2 and think about two vectors, then they are linearly dependent, means that they are just on the same direction. Okay. And yeah, so this is an example where C1x plus C1y equals to 0, then we see that the x is some multiple of y. Okay. And yeah, and when x is some multiple of y, then x direction and y direction will be different, and you feel that they will span the whole space because you take a linear combination of them, you can go to any point of this to a two-dimensional plane. Okay, and more geometric interpretation. If we are in 3 dimensions and have some x vector and y vector, and so just like a 2-dimensional case, they are linearly independent if they are not on the same line. Okay, And when they are not assigned line, then this origin and the x point and the y point will be three different point, will be 3 points that not line, and 3 points will determine a triangle and determine a plane. And if now you have the third vector, you want to see whether adding the third vector making those three vectors linearly dependent, then you want to check whether the third vector is a linear combination of those two vectors, because yeah, so back to here, I guess it's not quite. Yeah, we prove a little less, but basically because this thing, so we want to say basically because the linear dependent, then one of the vector will be linear combination of others, and actually you can prove something stronger. So any vector will be, so if you have a linear dependent, you can prove that. Not quite. Anyway, yeah. So kind of like this. Let's gloss over the detail. There is some funny detail. We have this. Okay. But anyway, so if you want linear independent, then so I guess logical side. If on linear dependent, then any vector is not the linear combination of others. So in particular, so this z vector cannot be a linear combination of x and y, and there will be outside of this plane. And yeah, and then if z is linear dependent on x and y, then it will be on this plane. Yeah, this is when x, y are not all 0. Okay, and yeah, so that's a geometric interpretation. If they are linearly independent, then x, y, z are on the same plane, and linearly independent, then x, y, z are not on the same plane, and they will span the whole R3. Okay. And okay, now we have more examples. So example that we can take a quiz. So whether the following vectors are linearly independent in R3. So first is so we see this before. So this is an example that we have the same number that we have from the spans. Okay, so yeah, I guess that's do a bit quicker because we will be short on time today. So yeah, so this thing was spanning the whole R3 with 3 vectors, and we kind of see from that, we kind of feel from that that it should be linearly independent. And in fact, it will be linearly independent, and let's do calculation. So we have a C1 vector 1 plus C2 vector 2 plus C2 vector 3 all equal to 0. And you solve this all equal to 0, and you see that you have C1, C2, 3 all need to be 0. And then second one, this is also linearly independent. Okay. Even though it doesn't span R3, but those two things are linearly independent because, well, you want this to be 0, then you see you only have a 1 here, so C2 equal to 0, and yeah, you only have a C1 here, and the C1 need to be 0. Yeah, so C1 equals C2 equals 0. And the third one, you want to see whether those things are linearly independent, and kind of because they don't span R3 and they have 3 vectors, then they are actually linearly dependent. Okay. And so you write down this all as equation, then you have this linear system equation for C1, C2, C3. So C1 with 1, 2, 4, and C2 with 2, 1. C1 with 1, 2, 4 here, and C2 with 2, 1, 3 here, plus C3 with 4 minus 1, 1 here, and they are A to 0. And then because this matrix is actually singular, and so this has a non-trivial solution. Yeah, this is from our theorem 1.5.2, where this square matrix equal to 0, and its matrix is singular, and so we have a non-trivial solution. Okay. And yeah, so those vectors are linearly dependent. Okay, and we can summarize from those 3 examples. We keep want to solve this equation of some linear equation of C equal to 0 and want to see whether they have a non-trivial solution. And as we said, this is exactly as our theorem 1.5.2. So now let's do special case first. So if we want to see our vectors, so you have exactly n vectors in Rn, and they want to see whether they are all linearly dependent. Then they are linearly dependent if only if x is singular. Okay, and remember from algebra 2, we also say x is singular means determinant of x equal to 0. Okay, that's our first theorem to determine where our vectors are linearly dependent. Okay, so the proof is the proof is basically we check this linear dependency equation. So c1x plus c2x plus cnx equal to 0. And as we always say, then we can write this as a linear system of equations as for C. So we have C times all those x, something equal to 0. And the matrix here, we see that the first column of this equation matrix is just our x1, and the second column is just x2, and the nth column is just xn. And so we can define this x matrix where every column of x is just our vectors. Okay, and I guess we didn't say here, but yeah. So this x here, I guess we didn't say, but x is but we already do our notation, so notation is a bit funny. So this x, we say it here, sorry. And yeah, so this big X is a matrix where every column of X is just corresponding vectors here. So X is x1 to xn. And this also satisfies our notation for matrix. Matrix before, where we say we have a big matrix X, then we can write each column vector as those color vector as a small case x. So small case 1, x1, small case x2 to small case xn is column vectors of big X. Okay, and yeah. Anyway, so we have those vectors, and we write this equation into linear system, and we see that it can be expressed as big X times the C vector. So we divide the C vector with just a column vector with C1 to Cn, and equal to this 0 vector. And we want the C to have a non-trivial solution, and we know that it's if only if X is singular. Okay, so this is from something from chapter 2 and theorem 1.5.2. Okay, and yeah, so then we know that x1 to xn is linear dependent if only if x is singular. Okay, and yeah, so we have a way to test whether some vectors are linearly independent. So we form a matrix from x, and then just calculate the determinant. So determinant equal to 0, x is singular, then they are linearly dependent. And the determinant is not 0, you are non-singular, they are linearly independent. But I guess once again, this only works for you have n vector, and we'll talk about more when you have more than n vector. Okay, and we have an example here, and you have 3 vector, you calculate determinant, and you see 0, so the vectors are linearly dependent. Okay, and yeah, then as we said, that only works for your number of vectors equal to the dimension of your vectors. Okay, and yeah, and so if you have some vectors in Rn but k not equal to n, then what should we do? Okay, so if n k not equal to n, then our matrix X is not a square matrix. Then you cannot calculate determinant, because the determinant is only defined on square matrix. Okay, and anyway, but we still have we can still write this equation. We still have this equation, and it's a homogeneous equation, and they always have a trivial solution. But we want to see whether it has other solution. Okay, and then yeah, we can check whether it has other solution by solving it more directly. So we just solve this equation, and we want to solve this linear system. We go back to chapter 1, and we go to make it into row echelon form. Okay, and from our analysis in chapter 1, we know that we have a non-trivial solution if only if our row echelon form has a free variable. Okay, and yeah, so this is what we do. We make it into row echelon form and see whether it has free variable. Okay, if it have yeah, if it's a free variable, then you have a non-trivial solution that you are linearly dependent. Okay? And if you don't have a free variable, then you don't have a non-trivial solution. You only have a c equal to 0 solution, and you are linearly independent. Okay, so you just check whether you have a free variable in your row echelon form. Okay? And then we also have some corollary here. So if the number of vectors you have is more than the dimension of your space, dimension of your Rn here, so if the number of vectors is more than its n here, then your vector must be linearly dependent, because you do go into row echelon form, then you see there must need to have some row echelon. So this should be, so wrong writing here, this should be n here and k here. So if k is bigger than n, and you just think about what the row echelon form should look like, you must have some free variable in between. Okay. Okay, and yeah, let's go quickly of one example. So you have 3 vectors here, and in 4 dimension, then you can run down this Cx equal to 0 equation, and they will have augmented matrix like this. So you have x1 here, x2 here, x3 here, and you make it into row echelon form, and you see that you have this free variable 0 here. Okay, you have a free variable 0 here, then you know that you have a non-trivial solution to this equation. So free variable being c3, and so x1, x2, and 3 must be linearly dependent. Okay, so that's how we can determine whether some vectors in Rn are linearly dependent. You make it into row echelon form. You write down this matrix and look at its row echelon form, see whether it has a free variable. Okay, so yeah, so this is kind of a corollary of how you find or extension of theorem 3.1.1. Okay, this is where you find how you find the some vectors are linearly dependent when the number of vectors is nothing as your dimension of your Rn. Okay, and then lastly we have another theorem on this linear independence. Theorem 3.3.2 says that you have a set of vector, and we say any vector inside our span can be written uniquely as a linear combination of those vectors. If only if our vectors are linear independent. Okay. So we are linear independent, then anything inside this span, so anything inside span already can be written as we say always be written as a linear combination of those vectors, because that's the definition of span. But this linear combination will be unique if our vectors are linear independent, and only if our vectors are linear independent. And yeah, so this will be a foundation of our next section on basis also. Okay, so this is very important. And okay, we have 5 more minutes. I guess we can go through the proof of this really quickly. So yeah, so you have I think we have 2 directions to prove. So first we will have something that can be written as so we have anything inside vector that can be always expressed as a linear combination. Okay, so I guess we have 2 things we want to prove, right? So let's mark this a bit. So we have uniquely as A and linear independent as B. Okay, and so first we I think here the first thing we'll do here is not A to not B. Okay, so not probably like this, not A to not B. So not A to not B, and so we assume that our linear combination expression is not unique. Okay, so so our V can be written as this linear combination with alpha, and they can also be written as a linear combination with beta. And we just take we just subtract those two equations, and V minus V becomes 0, and then we have alpha 1, those alpha minus beta as equations. Okay, and then because we say not every alpha equal to every beta because there are different expression. So one of those alpha minus beta is non-zero. Okay. So one of these alpha minus beta are non-zero. So so we have that. So if you define alpha minus beta as C, then one of the C is non-zero, and then we see that those vectors are linearly dependent. Okay. Okay. Yeah. I guess here we can just say let's do this not so convoluted. Okay, so here we can just define Ci equal to alpha I minus beta I, and then C is non-trivial. Okay, so we have not A to not B, and then we go then we go not B to not A. So if our vectors are not linearly dependent, sorry, if our vectors are linearly dependent, so not B to not A. So our vectors are linear dependent, so we have our favorite linear combination equation. So 0 equal to those C linear combination with non-trivial C, and so then we have so basically reverse this thing. Okay, and then we have one expression for some V. Okay, so if our V equal to some, so back to V equal to some alpha linear combination, then we can find another beta linear combination that's just beta equal to alpha plus C. And yeah, so we can have other linear combination with beta equal to alpha plus C. And because C is not all 0, then beta is not all equal to A. Okay. And so beta, so we have a beta not equal to A, and so this linear combination expression will be not unique. Okay, so we prove not B to not A, and not A to not B. So we know that condition A equal to condition B. Okay, so that's the final proof of this thing, and we finish this section just in time. Okay, so yeah, we have a checklist of 3.3. We have this minimal spanning set is a basis, and that's only if it's linear independent. Our vectors are linear independent, and we have a geometric meaning of a linear independent, and they also see that you want to see whether some vectors are linear independent. You can check whether this matrix X has linear independent. This matrix X is singular or not, or when it's not square. I guess we have need to have a HR here. So when X is not square, then we need to check the row echelon form. Okay, so we need to check whether the low echelon form has a free variable. Okay, and then we have a last theorem says that if our vectors are linear independent, then anything inside the span has a unique linear combination, if only. Okay, so yeah, that's for 3.3, and yeah, we will see you on next Wednesday, and we'll talk about basis. Okay.